In high-energy physics, the Tsallis statistics has been widely employed across various fields, with Tsallis-like distributions and phenomenological Tsallis distributions often used instead of exact distributions. These simple functions have successfully described experimental spectra of hadrons produced in relativistic heavy-ion collisions and proton-proton reactions at LHC and RHIC energies. This study derives exact and approximate hadron transverse momentum distributions for the Fermi-Dirac, Bose-Einstein, and Maxwell-Boltzmann statistics within the framework of the Tsallis statistics with escort probabilities, referred to as the Tsallis 3 statistics. The classical and quantum transverse momentum distributions are obtained in the zeroth term approximation and the quantum transverse momentum distributions in the factorization approximation introduced in the zeroth term approximation. Notably, the transverse momentum distributions in the zeroth term approximation and in the factorization approximation of the zeroth term approximation are identical in the Tsallis 3, Tsallis 2, and Q-dual statistics. The classical phenomenological Tsallis distribution exactly coincides with the classical transverse momentum distribution of the Tsallis 3 statistics in the zeroth term approximation, where the entropy of the system is zero in the whole range of state variables. However, the quantum phenomenological Tsallis distribution does not coincide with either the exact or approximate transverse momentum distributions of the Tsallis 3 statistics. The exact Tsallis 3 classical distribution and the classical phenomenological Tsallis distribution are applied to describe the experimental spectra of charged pions produced in proton-proton collisions at high energies. The values of the parameters T, Q, for both these model distributions differ in the whole energy range, indicating that the classical phenomenological Tsallis distribution is an unsatisfactory approximation for the exact classical transverse momentum distribution of the Tsallis 3 statistics. This research underscores the importance of accurately representing the Tsallis statistics in high-energy physics, as the use of simplifications can lead to inaccuracies in parameter estimation and interpretation of experimental data. In the realm of high-energy particle physics, Tsallis statistics plays a pivotal role in understanding transverse momentum distributions. This concept is applied through two distinct types of Tsallis-like distributions, classical and quantum. The classical Tsallis-like distribution, as presented in equation 5, is derived from the Maxwell-Boltzmann distribution, while the quantum Tsallis-like distribution, given in equation 6, is based on the Fermi-Dirac and Bose-Einstein distributions. The classical Tsallis-like transverse momentum distribution is applicable when the occupation number is described by the Maxwell-Boltzmann distribution, as indicated in equation 3. This distribution is a function of the transverse momentum, pt, rapidity, y, and temperature, t. In contrast, the quantum Tsallis-like transverse momentum distribution is applicable for different particle species, depending on whether they follow fermionic or bosonic statistics. Phenomenological Tsallis transverse momentum distributions, equations 7 and 8, are also derived from the Tsallis single particle distribution functions. These distributions are functions of the transverse momentum, rapidity, and temperature, and they too are applicable for different particle species based on their statistical properties. A crucial aspect of relativistic statistical mechanics is the multiplier A, which has been incorrectly defined in previous studies. The correct form of the multiplier A should be A equals V epsilon p, 2 pi, 3. This discrepancy is vital for accurately modeling particle production in high-energy collisions using Tsallis statistics. This page provides a comprehensive overview of the various Tsallis-like and phenomenological Tsallis transverse momentum distributions, their derivation, and their application in high-energy particle physics. It also addresses the significance of the multiplier A and its correct form in the context of relativistic statistical mechanics. Inconsistencies in Tsallis statistics are examined, with a focus on classical and quantum single-particle distributions derived from it. The reliability of Tsallis blastwave models is also called into question due to their dependence on these distributions. Notably, Tsallis-like distributions and quantum phenomenological Tsallis distributions do not correspond to the distributions of the Tsallis 3 statistics. The Tsallis statistics is formulated in three variants: Tsallis 1, Tsallis 2, and Tsallis 3. The first variant employs standard mean values, consistent with the normalization condition of probabilities. In contrast, the second variant utilizes generalized mean values, leading to inconsistencies between statistical mechanics, probability theory, and equilibrium thermodynamics. The third variant, Tsallis 3, incorporates normalized generalized mean values of the operators. Despite being based on the same generalized entropy, known as the Tsallis entropy, the three variants differ in their definitions of mathematical mean values of the operators. The paper argues that classical and quantum Tsallis-like distributions, as well as quantum phenomenological Tsallis distributions, lack a foundation in the fundamentals of statistical mechanics. This inconsistency has significant implications for the reliability of Tsallis blastwave models and the broader applications of Tsallis statistics. The Tsallis 1, Tsallis 3, and Q-dual statistics exhibit invariance under uniform shifts of the energy spectrum, whereas the Tsallis 2 statistics does not. In the grand canonical ensemble, exact transverse momentum distributions for massless particles have been calculated in the ultra-relativistic approximation using Tsallis 1 statistics. However, for relativistic massive particles, exact formulae for thermodynamic quantities can only be obtained in the integral representation. The Q-dual statistics have also been employed to calculate exact transverse momentum distributions. Tsallis 1 transverse momentum distributions have been successfully applied to describe experimental data of hadrons produced in proton-proton collisions at LHC and RHIC energies. A comparative analysis of the exact Tsallis 1 classical distribution and the classical phenomenological Tsallis distribution for massless particles in the ultra-relativistic approximation has been performed. The exact Tsallis 1 classical distribution for relativistic massive particles has also been derived. The primary objective of this study is to derive the exact Tsallis 3 transverse momentum distribution and apply it to describe the experimental transverse momentum spectra of hadrons created in proton-proton collisions at LHC and RHIC energies, a feat not previously achieved in high-energy physics. The Tsallis 3 statistics is often considered the most accurate, although the Tsallis 1 statistics is not inconsistent either. Another aim of this study is to derive the transverse momentum distribution in the zeroth term approximation of the Tsallis 3 statistics and compare it with the phenomenological Tsallis distribution. This study is organized as follows. Section 2 presents a new representation for the general formalism of the Tsallis 3 statistics. Section 3 derives the classical and quantum transverse momentum distributions. Section 4 describes the experimental data of hadrons, and Section 5 summarizes and draws conclusions. Throughout the paper, the system of natural units is used, where C equals K underscore B equals 1. The Tsallis 3 statistics, also known as the Tsallis statistics with escort probabilities in the grand canonical ensemble, is a new formulation of the generalized entropy and mean values of operators. This formulation uses the entropic parameter Q, which takes values between 0 and infinity, and reduces to the usual Boltzmann-Gibbs statistics when Q approaches 1. The thermodynamic potential omega is derived from the fundamental thermodynamic potential using the Legendre transform, and it includes terms related to the mean energy and number of particles in the system. The equilibrium probabilities are determined by the principle of thermodynamic equilibrium and the method of Lagrange multipliers. This study presents a comprehensive framework for generating summaries of complex research papers. The proposed approach leverages advanced natural language processing techniques to extract and condense critical information, ensuring that all major points are covered. The methodology involves a meticulous analysis of the original text, identifying key terms, concepts, and methodologies that are essential to understanding the research. Novel ideas, significant findings, and important arguments are highlighted, providing a clear and concise overview of the paper's contributions. Mathematical concepts, including equations and algorithms, are explained in detail, elucidating their purpose and significance in the context of the research. Data from figures, tables, and graphs are distilled into a compact and accessible form, preserving the essential information. To maintain continuity, connections to previous pages are established where applicable, ensuring a cohesive and integrated summary. Additionally, limitations, assumptions, and future work discussed in the original text are explicitly addressed, providing a comprehensive and nuanced understanding of the research. The resulting summary is tailored to expert researchers and stakeholders, employing a highly technical and professional tone that accurately conveys the complexity and depth of the original paper. The authors employ the gamma function formulae to rewrite the quantities in equations 21, 23, 24, and 25 in integral representation. This involves deriving the probability of microstates in integral form, resulting in equations 30 and 31 for q greater than 1 and q less than 1, respectively. These expressions use the gamma function, exponential functions, and the probability distribution PGI, beta, defined in equation 32. The probability distribution PGI, beta, is a function of the Boltzmann-Gibbs statistics, as seen in equation 33, which defines the partition function Zg, beta. The authors also define the grand potential omega g, beta, in equation 34, and the parameter beta, in equation 35. The norm equation 23 is rewritten in the integral representation, yielding equations 36 and 37 for q greater than 1 and q less than 1, respectively. These equations involve infinite summations and gamma functions, used to represent the probability distribution. This transformation facilitates the analysis of the Tsallis 3 statistics and its connection to the Boltzmann-Gibbs statistics. The authors introduce an alternative representation of the norm equation, a pivotal component in the Tsallis 3 statistical framework. This representation is expressed through infinite series, as seen in equations 38, 39, and 40, derived by applying the Taylor series expansion of the exponential function to the norm equation. Utilizing this representation, the generalized mean values of the Tsallis 3 statistics are rewritten in equations 41 and 42. These expressions are obtained by substituting the Taylor series expansion into the original definition of the generalized mean values, presented in equation 25. The resulting expressions involve infinite sums over the index n, where each term in the sum is a product of a gamma function, an integral over the variable t, and a power of the quantity beta, omega g, beta. The authors also introduce the notation, ta, and rit, which represents the mean value of the Boltzmann-Gibbs statistics, as defined in equation 43. This quantity is a function of the energy levels A and the chemical potential μ, and is used to express the generalized mean values of the Tsallis 3 statistics in terms of the corresponding mean value of the Boltzmann-Gibbs statistics. Equations 41 and 42 underscore the connection between the Tsallis 3 statistics and the Boltzmann-Gibbs statistics, demonstrating that the generalized mean values of the former can be expressed in terms of the mean value of the latter. This connection is a crucial aspect of the Tsallis 3 framework, and is essential for understanding the properties and applications of this statistical formalism. The calculation of the transverse momentum distribution for the Tsallis 3 statistics using a relativistic ideal gas of hadrons in the grand canonical ensemble is a complex process. It begins with the calculation of the thermodynamic potential and mean occupation numbers for the Boltzmann-Gibbs statistics in the grand canonical ensemble, focusing on the relativistic ideal gas. The norm functions lambda and theta for the Tsallis 3 statistics are derived from these calculations, which are then used to calculate the mean occupation numbers of the relativistic ideal gas in the grand canonical ensemble of the Tsallis 3 statistics. These calculations are performed for both q greater than 1 and q less than 1, resulting in two different expressions for the mean occupation numbers. For q greater than 1, the mean occupation numbers are expressed as an infinite series involving the gamma function, while for q less than 1, they are expressed as a contour integral involving the gamma function and the complex logarithm. These expressions demonstrate how the Tsallis 3 statistics can be applied to calculate the transverse momentum distribution of a relativistic ideal gas of hadrons, providing insights into the behavior of such systems under different statistical frameworks. This research contributes to our understanding of the statistical mechanics of complex systems, shedding light on the potential applications of non-extensive statistical mechanics in high-energy physics. Within the context of Tsallis 3 statistics, the transverse momentum distribution of particles is examined. The authors derive equations 49 and 50, which distinguish themselves from Tsallis 1 and Tsallis 2 statistics due to the presence of two norm functions, lambda and theta, as well as the function beta. These functions are solutions to a system of equations defined by EQs 36, 37, 39, 40, and 35. Notably, the Tsallis-like distributions 1, 5, and 6, and the phenomenological Tsallis distributions 2, 7, and 8, do not correspond to the exact transverse momentum distributions 49 and 50 of the Tsallis 3 statistics. This highlights the importance of accurately distinguishing between these different statistical frameworks. Furthermore, the authors provide the formula for the Maxwell-Boltzmann statistics of particles by taking the limit a to right-pointing arrow 0 in EQ 44, and integrating over the three-dimensional momentum p. This results in equation 51 for omega g beta. This calculation demonstrates the connection between the Tsallis 3 statistics and the Maxwell-Boltzmann statistics, a fundamental concept in statistical mechanics. In summary, this analysis provides a detailed examination of the transverse momentum distribution of particles within the Tsallis 3 statistical framework, contrasting it with other Tsallis distributions and providing a formula for the Maxwell-Boltzmann statistics of particles. The authors derive expressions for the normalization constant and the temperature parameter theta in terms of the modified Bessel function of the second kind, k nu, z, and the function beta, defined in equation 35. Substituting equation 51 into equations 36 and 37 yields equations 52 and 53, which are valid for q greater than 1 and q less than 1, respectively. These equations involve infinite summations over modified Bessel functions and gamma functions. The authors also derive expressions for the temperature parameter theta in terms of the modified Bessel function and the function beta. Substituting equation 51 into equations 39 and 40 yields equations 55 and 56, which are valid for q greater than 1 and q less than 1, respectively. These equations also involve infinite summations over modified Bessel functions and gamma functions. Furthermore, the authors derive an expression for the expectation value of the power law exponent, Tn, in terms of the temperature parameter theta and the modified Bessel function. Substituting equation 51 into equations 46 and 47, and taking the limit a to equals 0 yields equation 57, which is valid for q greater than 1. This equation involves an infinite summation over modified Bessel functions and gamma functions. Throughout these derivations, the authors utilize various mathematical concepts, including the gamma function, modified Bessel functions, and infinite summations. The parameter omega, defined in equation 54, plays a crucial role in these derivations, as it is used to simplify the expressions for the normalization constant and the temperature parameter theta. The paper explores the Maxwell-Boltzmann transverse momentum distributions for a gas of particles following Tsallis 3 statistics. To achieve this, two norm functions, lambda and theta, are introduced as solutions to a system of equations. These functions, along with beta and omega, contribute to the distinctness of the Tsallis 3 distributions from those of Tsallis 1 and Tsallis 2 statistics. The exact distributions are presented in equations 59 and 60, which differ significantly from classical Tsallis-like and phenomenological Tsallis distributions. The analysis also considers an ideal gas of massless particles in the ultrarelativistic limit, providing further insights into the properties of these systems under Tsallis 3 statistics. In the ultrarelativistic limit, where the mass approaches zero, the thermodynamic potential omega g beta is derived within the Tsallis 3 statistics framework. This potential is expressed in terms of the function beta, given by equation 35. The derived thermodynamic potential is then used to obtain equations for the particle and antiparticle densities, n and n, respectively, in both the q greater than 1 and q less than 1 cases. These densities are expressed as infinite series expansions involving the gamma function, which extends the factorial function to real and complex numbers. Furthermore, an equation for the temperature theta is derived in both the q greater than 1 and q less than 1 cases, also involving an infinite series expansion with the gamma function. This equation is crucial for understanding the thermal properties of the system. The expectation value of the product of the particle and antiparticle number operators, TNP sigma, and TNP sigma, respectively, is calculated by taking the limit of the parameter eta approaching zero and utilizing the previously derived equations for the thermodynamic potential and temperature. This comprehensive analysis of the thermodynamic properties within the Tsallis 3 statistics framework sheds light on the role of non-extensivity in statistical mechanics. The results are essential for further investigations into the behavior of particles and antiparticles under various conditions, providing a foundation for understanding the thermal properties of systems exhibiting non-extensive behavior. The authors present two distinct expressions for the Tsallis 3 statistics in the ultra-relativistic approximation, depending on whether Q is greater than 1 or less than 1. For Q greater than 1, the Tsallis 3 statistics is described by equation 67, involving a summation over n from 0 to infinity with terms comprising the ratio of gamma functions, exponential functions, and polynomial expressions in Q and epsilon p. Conversely, for Q less than 1, the Tsallis 3 statistics is given by equation 68, with modified gamma functions and polynomial expressions. By substituting equation 61 into equations 49 and 50, and taking the limit eta equals 0, the authors derive the transverse momentum distribution for both cases. For Q greater than 1, this distribution is expressed in equation 69 as an infinite summation, while for Q less than 1, it is given by equation 70 in terms of a contour integral. Both distributions are proportional to the product of GV, p squared, and t cosh, y, involving the gamma function, exponential functions, and polynomial expressions in Q, epsilon p, and other parameters. In the context of a relativistic ideal gas under Tsallis 3 statistics, the zeroth term approximation is employed to derive thermodynamic functions. The norm functions lambda and theta, solutions to a system of equations derived from Tsallis 3 statistics, are approximated as 0 and 1, respectively. Consequently, the entropy value is 0 for all temperatures and chemical potentials. The expectation values of the number operator are calculated using two integral representations, dependent on the parameter q. These integrals involve the function g, beta, defined in terms of particle energy epsilon p and chemical potential micro. By substituting the expression for g, beta, the integrals are simplified, yielding expressions for the expectation values that depend on whether Q is greater than or less than 1. Notably, the paper unifies the Bose-Einstein, Fermi-Dirac, and Maxwell-Boltzmann distributions into a single form using a series expansion. This unified representation is given by equation 78, where x represents the product of energy and inverse temperature, and eta is a parameter that takes on distinct values for each distribution. 1 for Bose-Einstein, 1 for Fermi-Dirac, and 0 for Maxwell-Boltzmann. The paper discusses the quantum mean occupation numbers in the zeroth term approximation for the Tsallis 3 statistics, derived from EQs 28, 29, and 7678. These are expressed as a series of infinite sums over k, with terms involving the parameter eta, which takes on values 1, 0, and 1, corresponding to Fermi-Dirac, Maxwell-Boltzmann, and Bose-Einstein statistics, respectively. For the quantum mean occupation numbers, the paper provides explicit expressions for eta equals 1 and eta equals 1, utilizing the Hurwitz zeta function zeta, s, a. The classical mean occupation numbers are also given in the zeroth term approximation, applicable to the Maxwell-Boltzmann statistics. Subsequently, the transverse momentum distribution of hadrons is derived using the Tsallis 3 statistics in the zeroth term approximation, with a similar form for all three types of particle statistics. This distribution is equivalent to those obtained for the Tsallis 2 and Q-dual statistics in the zeroth term approximation, as referenced in the paper. Finally, the quantum transverse momentum distributions in the zeroth term approximation are presented for 1 less than Q less than infinity, again utilizing the Hurwitz zeta function. These expressions are provided separately for eta equals 1 and eta equals 1, reflecting the different quantum statistics. The authors investigate transverse momentum distributions for Tsallis 3, Tsallis 2, and Q-dual statistics in the zeroth term approximation. The classical transverse momentum distribution is derived, revealing that it is identical in all three statistics, corresponding to the classical phenomenological Tsallis distribution. However, the entropy of Tsallis 3 statistics in the zeroth term approximation is zero for all temperatures and chemical potentials, rendering the classical phenomenological Tsallis distribution questionable in this context. The quantum transverse momentum distributions are also presented, with Tsallis 1 statistics yielding a distinct expression compared to the other two. Notably, the quantum phenomenological Tsallis distributions and quantum Tsallis-like distributions introduced in previous studies are not equivalent to the quantum transverse momentum distributions derived here. To simplify the quantum spectra in the zeroth term approximation, the factorization approximation is applied. This involves a mathematically unsanctioned replacement, leading to a modified expression for the quantum transverse momentum distributions. This section contributes to ongoing research in non-extensive statistical mechanics and its applications in particle physics, providing novel insights into the behavior of quantum systems under different statistical frameworks. In the factorization approximation of the zeroth term approximation for Tsallis 3 statistics, substituting equation 87 into equation 79, and applying the equation for the infinite geometric series yields the quantum transverse momentum distribution, 89. Notably, this distribution is identical for Tsallis 2 and Q-dual statistics due to the same quantum transverse momentum distribution in the zeroth term approximation. However, it deviates from the corresponding distribution in Tsallis 1 statistics. In contrast, the quantum Tsallis-like distribution and the quantum phenomenological Tsallis distribution do not correspond to the quantum transverse momentum distribution in Tsallis 3, Tsallis 2, and Q-dual statistics, as well as Tsallis 1 statistics. The form of the quantum distribution in Tsallis statistics can only be obtained in the factorization approximation, which is mathematically flawed. The authors investigate the applicability of the Maxwell-Boltzmann transverse momentum distribution in Tsallis 3 statistics to describe the experimental spectra of hadrons produced in high-energy proton-proton collisions. To derive the exact Tsallis 3 distribution, a system of two norm equations must be solved with respect to the norm functions lambda and theta. However, the integrals in these equations are nonconvergent due to the divergence of the integrands as t approaches zero, which is physically related to the infinite contribution of the Boltzmann-Gibbs thermodynamic potential at infinite temperature. In the limit t equals 1, beta, right pointing arrow infinity, the authors employ the series expansion, 38, to recast equations, 52, 55, and 59, as infinite series, featuring convergent integrals in select terms. To pinpoint these terms, they examine equations, 52, and 55, in the limit t right pointing arrow 0, where the integrands approximate to phi 0, n, t, tilde operator t caret, 2q, and phi 1, n, t, tilde operator t caret, 1q, yielding conditions for convergent terms. This leads to the maximal numbers of finite terms, denoted by n0 max and n1 max, as expressed in equation 91. However, not all finite terms are physical, prompting the introduction of a single upper cutoff limit of summation, n0, as a function of the fixed parameter nu. This ensures the correct Boltzmann-Gibbs limit and a unified description of the system of norm equations and statistical averages. The norm equations, 52, and 55, and the transverse momentum distribution, 59, for q greater than 1 can be rewritten as equations, 93, 94, and 95, respectively. The Maxwell-Boltzmann transverse momentum distribution of the Tsallis 3 statistics for q greater than 1 in the rapidity range y0 is less than or equal to y is less than or equal to y1 takes the form of equation 96. For numerical calculations, the authors set delta equals 0 in equation 92. Additionally, the zeroth term approximation of the Maxwell-Boltzmann transverse momentum distribution of the Tsallis 3 statistics is explored. In p plus p collisions at various energies, the Na-61 SHINE collaboration has measured the transverse momentum spectra of negatively charged pions. To describe these spectra, both the exact Tsallis 3 distribution and the phenomenological Tsallis distribution are employed. The exact Tsallis 3 distribution is calculated using EQ 86, which incorporates specific values of the scale parameter lambda, the temperature parameter theta, and the entropy parameter S. This approach yields a precise description of the experimental data. In contrast, the phenomenological Tsallis distribution serves as an approximation, providing a simpler yet still accurate representation of the spectra. The fitting results demonstrate a good agreement between the experimental data and both distributions, highlighting the efficacy of the Tsallis framework in capturing the underlying physics of P plus P collisions. Notably, the exact Tsallis 3 distribution offers a more nuanced description, particularly at high transverse momenta, where the phenomenological distribution deviates from the data. This study underscores the importance of precise modeling in understanding the complex dynamics of particle collisions, while also emphasizing the utility of phenomenological approaches in providing a simplified yet still informative representation of the data. The table presents the fitting parameters for the Tsallis 3 statistics in the context of pion production in proton-proton collisions at various energies, highlighting differences between the Tsallis 3 statistics and the phenomenological Tsallis distribution. The Tsallis 3 statistics show a higher temperature and larger radius compared to the phenomenological Tsallis distribution, with a parameter Q closer to unity. Figure 2 illustrates the transverse momentum spectra of pi and pi plus mesons measured by the Phoenix collaboration in proton-proton collisions at square root S equals 262.4 JV at mid-rapidity. The solid curves represent fits of the experimental data to the exact Tsallis 3 distribution, which is divided by the geometrical factor 2 pi pt. This equation, derived from the Tsallis 3 distribution, is used to calculate the particle yield as a function of transverse momentum, incorporating the geometrical factor, particle mass, and the Tsallis parameter Q. The integral in the equation represents the sum over all possible states, with the weight given by the Tsallis distribution. The result of this calculation is then normalized by the sum of the weights over all possible states, providing a probability distribution for particle production. This analysis demonstrates the application of the Tsallis 3 statistics in understanding particle production in high-energy collisions, showcasing its potential as a tool for describing non-equilibrium systems. The table presents parameters for the phenomenological Tsallis distribution, specifically the Tsallis 3 distribution in the zeroth term approximation, fitted to pion production data from various experiments. The data includes measurements from Na61, SHINE, Phoenix, and Alice collaborations at different energies, with the chemical potential set to 0. Each experiment's parameters, such as the temperature, radius, and the chi-squared value over degrees of freedom, are listed. Figure 2 from the Phoenix collaboration is also summarized, showing the transverse momentum spectra of pi and pi plus mesons measured at 262.4 JV. The data is fitted to the exact Tsallis 3 distribution and the phenomenological Tsallis distribution. The figure includes the experimental data and the fitted curves, highlighting the scaling factors for each line. This study compares the Tsallis 3 distribution and the phenomenological Tsallis distribution in describing the transverse momentum spectra of pi minus, pi plus, and pi plus plus pi minus mesons in proton-proton collisions at various energies. The experimental data are fitted to the phenomenological Tsallis distribution divided by the geometrical factor 2 pi pt, which is then multiplied by the total proton-proton cross-section. The fitted curves agree well with the experimental data, but the values of the fitting parameters for the phenomenological Tsallis distribution do not coincide with those of the exact Tsallis 3 distribution. At Phoenix energies, the temperature T of the Tsallis 3 statistics is approximately 114 MeV and 95 MeV for square root S equals 62.4 JV and square root S equals 200 JV, respectively. In contrast, the temperature T of the phenomenological Tsallis distribution is lower, approximately 92 MeV and 79 MeV, respectively. The radius r of the system and the parameter q also exhibit differences between the two distributions. The study also presents the transverse momentum spectra of pi minus, pi plus, and pi plus plus pi minus mesons measured by the Alice collaboration in proton-proton collisions at square root S equals 0.9 TeV and 7 TeV. The experimental data are fitted to the exact Tsallis 3 distribution and the phenomenological Tsallis distribution, with the fitted curves practically coinciding with each other. The values of the fitting parameters for both distributions are summarized in tables 1 and 2, respectively. The results suggest that the phenomenological Tsallis distribution underestimates the temperature of the Tsallis 3 statistics and overestimates the parameter Q, at Phoenix energies. However, the fitted curves for both distributions agree well with the experimental data, indicating that both distributions can describe the transverse momentum spectra of pi minus, pi plus, and pi plus plus pi minus mesons. The transverse momentum spectra of pi minus, pi plus, and pi plus plus mesons, measured by the Tsallis collaboration in pp collisions at square root s equals 0.9 TeV and square root s equals 7 TeV, are presented within the rapidity interval, y, less than 0.5. A comparison of the exact Tsallis 3 distribution and the phenomenological Tsallis distribution reveals that the exact Tsallis 3 distribution provides a better fit to the data, with distinct differences in the fitting parameters between the two models. At square root s equals 0.9 TeV, the exact Tsallis 3 distribution yields a temperature T of approximately 93 MeV, compared to 74 MeV for the phenomenological Tsallis distribution. The radius r of the system is approximately 5.0 fm for the Tsallis 3 statistics, whereas it is 4.7 fm for the phenomenological Tsallis distribution. The parameter Q is approximately 1.10 for the Tsallis 3 statistics, compared to 1.15 for the phenomenological Tsallis distribution. Similar differences are observed at square root s equals 7 TeV, where the exact Tsallis 3 distribution exhibits a higher temperature and radius compared to the phenomenological Tsallis distribution. These results suggest that the exact Tsallis 3 distribution is a more accurate description of the transverse momentum spectra of pi mesons in pp collisions at high energies. The authors present a comparative analysis of the Tsallis 3 distribution and the phenomenological Tsallis distribution in describing transverse momentum spectra of pi plus plus pi minus mesons. The analysis uses experimental data from the Tsallis collaboration, collected in pp collisions at a center of mass energy of square root s equals 2.76 TeV within the rapidity interval, y, less than 0.8. Both distributions are fitted to the experimental data, with the results displayed in Figure 4. The fitting parameters for each distribution are summarized in tables 1 and 2. The curves representing the two distributions practically coincide, indicating both provide a good description of the experimental data. However, a discrepancy emerges when comparing the fitting parameters of the phenomenological Tsallis distribution to those of the exact Tsallis 3 transverse momentum distribution. This discrepancy suggests that the temperature and parameter Q of the phenomenological Tsallis distribution underestimate and overestimate, respectively, the corresponding values in the Tsallis 3 statistics at Tsallis energies, square root s equals 0.9 and 7 TeV. The results for pi minus at the Tsallis energy square root s equals 0.9 TeV obtained by the phenomenological Tsallis distribution are nearly identical to those found in Ref. 23. Reinforcing the validity of the Tsallis 3 distribution as a suitable model for describing particle production in high-energy collisions. In particle collision experiments, a comparative analysis of the Tsallis 3 statistics and the phenomenological Tsallis distribution is presented, focusing on the energy dependence of the temperature T for pi minus, pi plus, and pi plus plus pi minus mesons produced in pp collisions, specifically in the energy range from 6.3 GeV to 7 TeV. Both distributions are used to model the particle spectra obtained from these collisions. The exact Tsallis 3 distribution and its phenomenological counterpart, an approximation of the zeroth term, are compared in terms of their temperature T values. At the energy square root s equals 2.76 TeV, the phenomenological Tsallis distribution underestimates the temperature T of the Tsallis 3 statistics, with T tilde operator 100 MeV for the Tsallis 3 statistics and T tilde operator 84 MeV for the phenomenological Tsallis distribution. Similarly, the radius r of the system is higher for the Tsallis 3 statistics, r tilde operator 5 fm, compared to the phenomenological Tsallis distribution, r tilde operator 4 fm. The non-extensivity parameter Q also differs, with Q tilde operator 1.08 for the Tsallis 3 statistics and Q tilde operator 1.15 for the phenomenological Tsallis distribution. Figure 5 illustrates the energy dependence of the temperature T for both distributions across the specified energy range, highlighting the discrepancies between the two distributions in terms of temperature and non-extensivity parameter. The solid points represent the results of the fit for the Tsallis 3 statistics, while the open points represent the phenomenological Tsallis distribution. This comparison suggests that the phenomenological Tsallis distribution does not accurately approximate the exact Tsallis 3 distribution at higher energies. The limitations of the phenomenological Tsallis distribution in modeling particle spectra at high energies are discussed, emphasizing the importance of considering the exact Tsallis 3 statistics for more accurate representations of the temperature and non-extensivity parameter. The momentum distribution of the Tsallis 3 statistics in the zeroth term approximation is described, highlighting the difference in temperature between the phenomenological Tsallis distribution and the Tsallis 3 statistics across the entire energy range. The temperature of the phenomenological Tsallis distribution is shown to underestimate the temperature of the Tsallis 3 statistics. Figure 6 illustrates the energy dependence of the radius r for the Tsallis 3 statistics and the phenomenological Tsallis distribution for pi minus, pi plus, and pi plus plus pi minus mesons produced in pp collisions. The values of the radius r for both models are compared, showing a difference that increases with the energy of collision, except at energies up to 0.9 TeV where the values are compatible with an error uncertainties. The energy dependence of the entropic parameter Q of the Tsallis 3 statistics and the phenomenological Tsallis distribution for pi minus, pi plus, and pi plus plus pi minus mesons produced in pp collisions across an energy range of 6.3 GeV to 7 TeV is illustrated in Figure 7. The parameter Q values for the Tsallis 3 statistics and the phenomenological Tsallis distribution are compared, showing that the phenomenological Tsallis distribution overestimates the parameter Q of the Tsallis 3 statistics, with the difference increasing with energy. Both models exhibit the same trend behavior, with the parameter Q values deviating significantly from unity, increasing with square root s, indicating a departure from the Boltzmann-Gibbs statistics. The Tsallis 3 statistics and the phenomenological Tsallis distribution are fitted to the transverse momentum distribution of the mesons, demonstrating that the parameter Q of the phenomenological Tsallis distribution does not approximate well the parameter Q of the Tsallis 3 statistics. The energy independence of the statistical distributions of pions is observed, consistent with previous findings. This research delves into the transverse momentum distributions of hadrons within the context of Tsallis 3 statistics. It juxtaposes its findings with the phenomenological Tsallis distribution, an approximation of the exact Tsallis 3 distribution. The study is conducted at three distinct center of mass scattering energies: 17.3 GeV, 0.9 TeV, and 7 TeV. The outcomes suggest that the phenomenological Tsallis distribution inadequately estimates the parameters T, Q of the exact transverse momentum distribution of the Tsallis 3 statistics. Both models exhibit a similar trend in the values of the parameters as functions of the center of mass scattering energy, but the discrepancies in the values of the temperatures T and the parameters Q of both these models indicate the limitations of the phenomenological Tsallis distribution as an approximation of the exact Tsallis 3 distribution. At a center of mass scattering energy of 17.3 GeV, the difference between the temperatures of the Tsallis 3 statistics and the phenomenological Tsallis distribution is 44.95 plus or minus 9.50 MeV, with the phenomenological Tsallis distribution temperature being lower than the Tsallis 3 statistics prediction at the level of 4.7 sigma. The difference between the parameters Q is 0.0338 plus or minus 0.0210, with the phenomenological Tsallis distribution parameter Q being higher than the Tsallis 3 statistics prediction at the level of 1.6 sigma. At a center of mass scattering energy of 0.9 TeV, the difference between the temperatures of the Tsallis 3 statistics and the phenomenological Tsallis distribution is 18.60 plus or minus 3.19 MeV, with the phenomenological Tsallis distribution temperature being lower than the Tsallis 3 statistics prediction at the level of 5.8 sigma. The difference between the parameters q is 0.0487 plus or minus 0.0053, with the phenomenological Tsallis distribution parameter q being higher than the Tsallis 3 statistics prediction at the level of 9 sigma. Lastly, at a center of mass scattering energy of 7 TeV, the difference between the temperatures of the Tsallis 3 statistics and the phenomenological Tsallis distribution is 27.58 plus or minus 2.55 MeV, with the phenomenological Tsallis distribution temperature being lower than the Tsallis 3 statistics prediction at the level of 10.8 sigma. The difference between the parameters q is 0.0621 plus or minus 0.0036. With the phenomenological Tsallis distribution parameter q being higher than the Tsallis 3 statistics prediction at the level of 17.5 sigma. In conclusion, the study highlights the limitations of the phenomenological Tsallis distribution as an approximation of the exact Tsallis 3 distribution, particularly in terms of temperature and parameter q. The results underscore the importance of using exact analytical expressions for transverse momentum distributions of hadrons in the framework of Tsallis 3 statistics. The authors introduce a novel general formalism for the Tsallis 3 statistics in the grand canonical ensemble, which is equivalent to other formulations of the Tsallis 3 statistics. This formalism allows for the calculation of the probability distribution of microstates from the principle of thermodynamic equilibrium, expressed as a function of two norm functions that are solutions to a system of two norm equations. The authors present exact analytical results for the probability distribution, norm equations, and statistical averages in both integral representation and series expansion. They also derive the transverse momentum distributions of the Tsallis 3 statistics for Fermi-Dirac, Bose-Einstein, and Maxwell-Boltzmann statistics of particles, expressed in both integral representation and series expansion. The terms of the series expansion for the Maxwell-Boltzmann statistics are given explicitly in terms of the modified Bessel function of the second kind. The Maxwell-Boltzmann transverse momentum distribution is obtained for both relativistic massive particles and massless particles in the ultra-relativistic approximation. Furthermore, the authors calculate analytical expressions for the transverse momentum distributions of hadrons for the Tsallis 3 statistics in the zeroth term approximation for Fermi-Dirac, Bose-Einstein, and Maxwell-Boltzmann statistics of particles, as well as in the factorization approximation of the zeroth term approximation for Fermi-Dirac and Bose-Einstein statistics of particles. It is found that the classical and quantum transverse momentum distributions in the zeroth term approximation and the quantum transverse momentum distributions in the factorization approximation of the zeroth term approximation are the same in the Tsallis 3, Tsallis 2, and Q-dual statistics. In the zeroth term approximation of the Tsallis 3 statistics, the entropy of the system is zero for all values of the temperature, volume, chemical potential, and entropic parameter Q. The authors also show that the phenomenological Tsallis distribution for the Maxwell-Boltzmann statistics of particles, widely used in high-energy physics, exactly coincides with the Maxwell-Boltzmann transverse momentum distribution in the zeroth term approximation for the Tsallis 3 statistics. This implies that the classical phenomenological Tsallis distribution is an approximation distribution for the classical exact Tsallis 3 distribution and corresponds to the unphysical condition of zero entropy of the system in the Tsallis 3 statistics. The authors of this research paper apply the exact Maxwell-Boltzmann distribution of the Tsallis 3 statistics for Q greater than 1 to analyze experimental data on hadrons produced in proton-proton collisions at high energies. However, they find that the Tsallis 3 distribution for Q greater than 1 is divergent and introduce an upper cutoff limit of summation to regularize it. This study compares the numerical results of the classical phenomenological Tsallis distribution, which is the zeroth term approximation of the Tsallis 3 statistics, with the exact Tsallis 3 distribution. Both distributions are applied to describe the experimental data on charged pions produced in proton-proton collisions at high energies. The fitting parameters of the exact Tsallis 3 distribution and the phenomenological Tsallis distribution are found, and their values are compared as functions of collision energy. The values of the volumes, radii r, for both distributions are compatible with an error in certainties up to 0.9 TeV. However, the values of the temperature T and the parameter Q of the phenomenological Tsallis distribution deviate from those of the exact Tsallis 3 distribution in the whole energy range. This suggests that the classical phenomenological Tsallis distribution is an unsatisfactory approximation for the exact classical transverse momentum distribution of the Tsallis 3 statistics. The authors acknowledge support from the RSCF grant and the Romanian Ministry of Research, Innovation, and Digitalization. All data supporting the findings of this study are included within the article. In Appendix A, the mean number of particles in the system is defined as n equals summation display p sigma in bracketly tnp sigma in bracketry ht, where in bracketly tnp sigma in bracketry ht is the mean number of particles with momentum p and the third projection of the spin sigma. The momentum of a particle is then described, setting the stage for further analysis. In the context of relativistic quantum systems, the quantization of pi is intricately linked to the volume of the system. This relationship is encapsulated in the integral equation for n, which features the relativistic invariant distribution and the multiplier a. The relativistic invariant distribution is a crucial component, as it ensures that the physical laws governing the system remain unchanged under Lorentz transformations. To derive the differential particle number distribution, hyperbolic coordinates are introduced, accompanied by their corresponding measure. This facilitates the calculation of particle distributions in the relativistic regime. The measure of hyperbolic coordinates is defined as the invariant volume element, which is essential for maintaining Lorentz invariance. The differential particle number distribution is subsequently derived, revealing the underlying structure of particle production in relativistic systems. A key aspect of this distribution is its connection to the Lorentz invariant transverse momentum distribution, which describes the momentum distribution of particles produced in high-energy collisions. Ultimately, the differential cross-section for particle production is obtained, providing a fundamental tool for understanding the dynamics of relativistic systems. This quantity is crucial for making precise predictions about particle production rates in high-energy collisions, such as those encountered in particle accelerators. Throughout this analysis, the connections to previous discussions on relativistic invariance and particle production are maintained, ensuring a cohesive understanding of the underlying physics. The Tsallis 3 statistics, a statistical mechanics framework used in complex systems, is represented in two equivalent forms. These representations are derived from equations 19 and 20 of the main text, resulting in equations b.1 and b.2. In these equations, z denotes a normalization constant, theta represents an unknown quantity, and bracketly th, and bracketry ht and bracketly tn, and bracketry ht are statistical averages of the Hamiltonian and number operators, respectively. To determine the probability distribution, the authors solved two norm equations. The first norm equation is obtained by equating equations b.2 and b.4, as shown in equation b.5. The second norm equation is derived by rearranging equation b.6, which involves the statistical averages of the Hamiltonian and number operators. Once these norm equations are solved, the probability distribution b.1 and the statistical averages can be determined. The statistical averages are expressed in equation b.7, which is equivalent to the probability distribution 21 in the main text. In summary, this page presents an alternative representation of the Tsallis 3 statistics, providing a different perspective on the statistical mechanics of complex systems. It also outlines the process of solving norm equations to determine the probability distribution in statistical averages, ultimately connecting back to the original probability distribution 21. In the realm of statistical mechanics, the Tsallis 3 statistics have been re-expressed in an alternative representation, providing a new perspective on this complex field. The probability distribution, denoted by pi, is rewritten as a function of the normalization constant z, and the modified inverse temperature parameter beta, asterisk operator. This representation is compared to the canonical ensemble for the Tsallis 3 statistics, as presented in reference 2, highlighting the equivalence between different representations of these statistics. In high-energy physics, traditional statistical mechanics often falls short in describing real-world phenomena, which frequently exhibit non-equilibrium and long-range correlations. Non-extensive statistical mechanics addresses these complexities by introducing a new parameter, Q, that quantifies the degree of non-extensivity. This framework is built around the concept of Tsallis entropy, which is related to the traditional Boltzmann-Gibbs entropy. The Tsallis distribution, a power law distribution derived from maximizing Tsallis entropy under certain constraints, has been successfully applied to describe particle spectra in high-energy collisions. This distribution provides a better fit than traditional statistical distributions, as demonstrated by analyses of experimental data from NA61, SHINE, Phoenix, and ALICE collaborations. Superstatistics, a statistical framework that combines different distributions to describe complex systems, can be used to derive the Tsallis distribution and other non-extensive distributions. This highlights the versatility of non-extensive statistical mechanics in understanding complex systems. Theoretical discussions are complemented by a detailed analysis of experimental data, demonstrating the efficacy of non-extensive statistical mechanics in describing particle production in spectra. The Tsallis distribution provides a good fit to the experimental data, emphasizing the potential of non-extensive statistical mechanics to provide insights into quantum systems and their behavior. The connection between non-extensive statistical mechanics and quantum mechanics is explored, highlighting the potential for non-extensive statistical mechanics to provide new insights into quantum systems. The paper concludes by emphasizing the importance of non-extensive statistical mechanics in understanding complex systems, both in high-energy physics and beyond, and identifies the need for further research to fully explore the potential of this new statistical framework.